Now we'll see about refraction of light. What is a refraction of light means when light ray enter from one medium to other medium, its path little bit changes, that is it bends at the interface of the mediums. Suppose you see, you can take interface of the two mediums and interface AB, and I draw here a normal N. If the light ray incident with an angle I, incident angle they measured with respect to normal. So incident angle is I, which is fall like this. If there is no medium change, so it will go straight without any bending or deviation. But because of medium changes, it bends sometimes towards to the normal or sometimes away from the normal, and depend upon the way to where it travel. That is rarer to denser or denser to rarer. That we'll see in the next concept. Suppose you can take this is a rarer to denser. You can take rarer to denser means it bends towards to the normal. This angle what we call angle of refraction. The light ray bends towards to the normal. Now we'll see some properties of refraction. Suppose here you see this is the incident ray, normal and refracted ray. All three must be in the same, it should be in the same plane. That is the first rule or first law. The incident ray, normal and refracted ray should be in the same plane. And second one, the ratio of sine of incident angle to sine of refracted angle is equal to constant. That constant they represent with mu. The mu is called refractive index. So sine of incident to sine of refracted angle is equal to constant for any pair of mediums. So that is equal to refractive index of the pair of the mediums. What is a refractive index? For example, you can take a refractive index represent with mu, that they define as speed of the light in vacuum to speed of the light in that medium. This is what we call absolute refractive index. Speed of the light in vacuum to speed of the light in that medium. Suppose what is relative refractive index? A relative refractive index means suppose when light enter from first medium to second medium. So this you can think first medium and this is second medium. So you can write mu12. If light enter from first medium to second medium, they represent like this. Mu12 is equal to mu2 by mu1. It is mu2 by mu1. This is what we call a relative refractive index. So how we get relative refractive index? For example, you can take mu1 is equal to speed of the light by v1, velocity in that medium. And what is mu2? Mu2 is c by v2. From these two equations, what you can write? Mu2 by mu1 is equal to v1 by v2 we can write. So from this relative refractive index of a pair of mediums, how we can define? It is a ratio of speed of the light in the mediums. Of course, you can write mu2 by mu1 is equal to v1 by v2, reverse ratio we get. From one medium to other medium, what factor changes? For example, you can take here, and the speed of the light in a medium is v is equal to, you can write nu lambda. V is a speed of light, and nu is frequency and lambda is wavelength. From one medium to other medium, if light is going, then there is no change in the frequency, only velocity and wavelength changes. So here what you can write, velocity v is proportional to lambda, but we know velocity v is inversely proportional to refractive index. From that formula you see that v is proportional to c by mu. So from that v is proportional to 1 by mu we can write. So from this what do you get relation? Velocity speed of light in two mediums ratio is equal to lambda 1 by lambda 2, that is equal to mu2 by mu1. We get a reverse ratio for refractive index. From this, what do you say? If any medium is there which is a light is traveling from rarer to denser, denser means more refractive index is there, that what you call denser media. So if rarer to denser it is going, then what happened to wavelength? Wavelength decreases. Speed also decreases, but frequency remains constant. But one important point, for a given media, speed of the light is constant, but frequency and wavelength can change. So in that case, V is constant, and nu and lambda can adjust. For a given medium medium changes means speed changes and wavelength also changes. Frequency constant for given type of color or given light. Given light means a given color. Of course, color changes, frequency also changes. So for given color, suppose if you are sending a monochromatic beam from one medium to other media, frequency is not changing, wavelength changes and velocity changes. In a given media, you can take different colors. Different colors means you can say different frequencies. Wavelength adjusts, wavelength changes, but and the speed of light will be same for a given media. Those two are important points here. Okay. But based on the wavelength, a small change is there in the refractiveness of the medium, that they give a relation like this: mu is equal to some constant a plus b by lambda square. That variation is very small. That's why they didn't take that variation. They mentioned they treat that all wavelengths, all frequencies in a given media are traveling with the same speed. So refractive is also same, but a slight difference is there. So mu is equal to a plus b by lambda square. From this, which is having more lambda, that has less refractive index. So which color having more wavelength? Which color having more wavelength? That is lambda of red is greater than lambda of yellow color is greater than lambda of violet. From this, what you can write? Mu of red is less, mu of yellow is less, mu of violet is higher when compared to this. But that variation is very small. That's why for a given medium, all the colors have same refractive index they took. But we have one concept, dispersion. And while discussing about dispersion concept, we will discuss about what is a variation and which has high wavelength and which is having less wavelength, how refractive index changes. There we discuss. Okay. Based on electromagnetic theory, how speed of the light changes from medium to medium, that we'll see. According to electromagnetic theory, they gave that speed of the light in vacuum is square root of 1 by square root of mu naught epsilon naught. See, speed of the light in vacuum, mu naught permeability of the medium, and that we get in magnetism chapter, and epsilon naught in electrostatics we get that permittivity of the free space. So these two are permeability and permittivity of the vacuum. So C is the speed of the light in the vacuum. Suppose if you take any other medium, suppose V is equal to, for other medium we can write mu epsilon. What is mu? Mu is the permeability of that medium and epsilon is the permittivity of the medium. And that we can write as like this, square root of mu we can write a relative permeability into permeability of the free space. And epsilon also we can write a k, dielectric constant, into permeability of permittivity of free space we can write like this. From this you can take common here, in place of 1 by square root of mu naught epsilon naught we can write as C. So this total you can write C by square root of mu r into k. So from this, how you define refractive index? So what is the absolute refractive index? Refractive index is mu is equal to speed of the light in vacuum by speed of the light in that medium. That's what you call absolute refractive index. So speed of the light in vacuum, C by V. From this formula, what you can write? C by V, that is square root of mu r into k. This mu is refractive index, this mu is permeability, don't get confused. And mu is refractive index, mu r is permeability, relative permeability, and k is dielectric constant of the medium. This how we get relation. Now see about Snell's law. What is Snell's law means? A sine of incident angle that already we discussed by sine of refracted angle is equal to constant. Constant means we can take refractive index here. Suppose if light enter from first medium which is having refractive index mu1 and second medium have refractive index mu2, it enter into mu2 medium. Then what you can write here, that is mu1 to 2, that we can write as mu2 by mu1 we can write. Sine of incident by sine of refraction is equal to mu2 by mu1 we can write. Suppose if you want to represent it vector notation, and for very small angles you can take a sine I is equal to I, sine R is equal to R, and if you want to represent with vector, so you can take like this. So I cross n cap into mu1, you send this mu on that side, this side R cross n cap into mu2. If you take unit vector along incident line, incident ray, and normal on the surface, that is n cap and I cap. Along refraction ray, if you take unit vector, that is R cap into n cap. So like this we get. Suppose if you want to check whether these two are representing same direction or not, well, because cross product or vector product means it gives a direction. So to check that, apply right hand screw rule. Suppose if I is like this, you see that I is fall like this, I like this, and n is like this, normal going like this. So that is I and n cap. Apply right hand screw rule. So how these vectors are rotating in anti-clockwise direction, like this they are going. So thumb shows the direction of the cross product. So this is coming out of the board, so it shows a dot. Coming out of the board means dot we can take. Into the board means they represent with cross. Now about R cross N. R is like this, of course, like similar to I only, like this we get. Small changes there, and normal is like this, n cap. So here also we get, and out of the board only. Both are showing in the same direction. So this is a vector representation of Snell's law if angle of incident and refraction are very, very small. Now we'll see about refraction of light when it enter from rarer to denser and denser to rarer. Suppose you can take this the interface of the two mediums, and this is a rarer medium and this is the denser medium, and this is a normal drawn, and a light ray incident with respect to normal with some angle here. You can think angle of incidence is I, and this is normal. When it enter from rarer to denser, what happens? Suppose medium change is not there, it should go straight like this. But because of change in medium, what happened? Here it bends towards to the normal. Light ray enter from rarer to denser, it bends towards to the normal. So you can take like this. This is the angle of refraction. So light enter from rarer to denser, and light ray bends and refracted ray bends towards to the normal here. What is the deviation? During this process it has some deviation. What is the deviation in this process? This is the how much angle it changes. Actually, this total angle is I, same as this opposite angle, and now it is making refracted ray make an angle R only. Then what is the deviation? That is I minus R. When light ray enter from rarer to denser, it bends towards to the normal. Other one, the deviation is I minus R. Instead of going like this, it goes like this. So how much deviation is there? I minus R. Same thing if you take when light ray enter from denser to rarer. Denser to rarer. See that? This is denser and rarer. What happened? Light ray enter from denser to rarer. And same thing, they bend towards to the normal. Here it bends away from the normal. This is the actual path it has to follow. Instead of that, it going like this. This is the angle of incidence. This is the angle of refraction. But what is actual angle of actual angle if there is no medium change? This is the angle of incidence I, opposite angle. These two are opposite angles. So now what is the deviation in this case? In this case, deviation d is equal to r minus I, because here r is greater than, here I is greater than r, but here r is greater than I. So when it is possible, when light enter from mu1 to mu2, so we can write mu1 to 2 is equal to mu2 by mu1 greater than 1, because and second medium has a refractive index mu2, which is a denser, so we can write mu2 is greater than mu1. Here what is say mu2 to 1, that is mu1 by mu2, that is here less than 1 you can take. But absolute refractive index never be less than 1. Why? Because light travel with a high speed in a vacuum only, and no other medium which is having speed more than the light speed in the vacuum. So which is having less refractive index, that is vacuum only, that is having 1. Less than 1 not possible. But why we are getting there less than 1 means here light travel from denser to rarer. That's why we have to take a reverse. It is a relative refractive index only. Yes, relative refractive index can be less than 1 or greater than 1. But absolute refractive index, any refractive index of any medium compared with vacuum means vacuum only having less, that is 1. So remaining having more value only. So it should be greater than 1 only here. So here, and rarer to denser means it bends towards the normal, and denser to rarer means it bends away from the normal. Here deviation is I minus R, there deviation is R minus I. Here refractive greater than 1, here refractive is less than 1. Now we'll see different cases. Suppose for example, this is the interface of the two mediums, and refractive index of this one is mu1 and this is mu2. You can take a denser or rarer, any one you can take. And this is a normal drawn on the surface. If light ray incident along the normal, suppose if it is going like this, along the normal only, then what is angle of incidence? I is equal to 0. Because we are measuring angle of incidence with respect to normal only. Then angle of refraction also we get 0. Here there is no bending of light we are observing. See here R is equal to 0 we get. Even medium change is there. If the angle of incidence is perpendicular to surface or 0 degrees with respect to normal, that what you call angle of incidence is 0 degrees. Then refraction also we get 0 degrees. Without bending it can enter into other medium. Normal incidence means. So other case, suppose you can take even angle of incidence is not equal to 0, and even though light ray go without any bending, suppose it is going like this means what you can say, the refractive index of first medium and refractive index of second medium both are equal. This is mu and this also equal to mu. So mu1 is equal to mu2. If there is no medium change, what happened? There is no bending of light, so there is no refraction. So it can go straight. Here angle and refracted angle are equal here. Both are same we get. Other case, suppose if light ray enters here, this is a interface of the two mediums, and this is a normal drawn, and the ray of light is incident on the medium here with an angle I, and there is a beam of reflected ray. You know what is angle of reflection? That is I only again, because angle of reflection and refraction and incident and reflected same, but refraction is different. Suppose you can take refraction is like this. This is R. Don't take here R. Already we use R for refracted ray, so that's why both are equal. Now that's why we can take I only. Suppose you can assume a situation, the angle between a reflected ray and refracted ray is 90 degrees. So then what is a refractive index of the medium? The refractive index of the medium mu is equal to what you can write. Suppose it enter from A to some medium. Here refractive index is 1 you can take. For air or vacuum almost they took as 1. Why? Because you see refractive index of the vacuum is 1 and refractive index of the air is 1.0003. Like this we get as a small change is there. Of course for refractive index of the water 4 by 3 nothing but 1.33. Refractive index of the glass that is 3 by 2 nothing but 1.5, and refractive index of the diamond is 2.6 or 2.5 we get. So these values you have to remember all this. So vacuum and air both are same only, so almost both we are taking as 1 only, and water and glass, diamond. Okay, refractive index increases means what do you say? Denser mediums. So rarest media are rarer media, and that is a vacuum only. Suppose if light enter from vacuum or air to other medium which is having refractive index mu, and then here the angle between reflected ray and refracted ray is 90 degrees. Then what you can write refractive index mu? Mu is equal to sine of incidence. Sine of incidence by sine of refraction. What is the relation between I and R? You see this total. You see this total angle is 180. In that here 90 gone. And what about this R? R is equal to 90 minus I. This total angle, once you see, this total angle is 180. In that here 90 gone. And remaining I plus R is equal to 90. So R is equal to what you can write? 90 minus I. So from that what you can write sine of incident by sine of 90 minus I is equal to sin I by cos I, that is equal to tan I. So the refractive index of the medium is equal to tan I we can write. In which case if the reflected ray and refracted ray are, this is incident ray, reflected and refracted ray are making 90 degrees each other, then refractive index of the medium we can write mu is equal to tan I. Now you see one of the application of Snell's law. Suppose if a light is refracted through different mediums, so see that here refractive index mu 1, mu 2, mu 3, mu 4, like that it changes. Then ray is refracted like this, incident with an angle I and refracted with R1. Again on second surface it incident with R1. Reason these two are parallel lines, parallel surfaces, and these are transverse lines. So alternate angles are equal, R1. Refracted to into next medium, that is R2, here R2, R3, R4, like that. Refractions, and when medium change is there, different refractions we are getting. According to Snell's law, suppose if only two mediums are there, this is mu1 and this is mu2, and this is a normal light ray incident with some angle I and refracted into the second medium with an angle R. Then what you can write? Mu2 by mu1 is equal to sine of incidence by sine of refracted. So from this what you can write? Mu2 sine R is equal to mu1 sine I we can write. That means refractive index of the medium, you see what you get, refractive index of mu first medium into sine of angle in the first medium is equal to refractive index of the second medium into sine of angle in that medium, like that we can write. So similarly what you can write from here, that is refracting to the first medium is mu sin I is equal to, for second medium what you can write, mu1 sin R1, mu2 here between these two, mu2 here sin R2 is equal to mu3 sin R3. Like this we get mu4 sin R4 is equal to you get constant. So suppose if finally the ray come into the same media as this, suppose if mu4 is equal to mu, then what you get? Mu4 is equal to mu. So from that what you can write? Mu4 is equal to mu, then the first equation, that is mu sin I is equal to, and last one, that is mu4 sin R4 we get. Suppose if these two are equal, mu4 and mu, that means finally the ray come into the same medium as first where it comes. So suppose if it is mu, then what you can write? Mu we can write, mu get cancelled, sin I is equal to sin R4. So if mu is equal to mu4, we can write I is equal to R4. That means with what angle of incidence takes place here, with the same angle finally it refracted back into the same medium. If medium is same, it will be refracted with same angle. So I is equal to R4 we get. That means what is here angle? This also we get I, if it is equal to mu means. This is one of the application. Now you see what is optical path. Optical path means, for example, you can take light travel in vacuum some distance, that is L distance you can take. With what speed it is moving? With the speed of light in vacuum c, which is equal to 3 into 10 power 8 meters per second. So how much time it take to travel that much distance? The time taken to travel is L by c. Within the same time in other medium, so within the same time in other medium, how much distance the light travel? That you can take length of the medium Lm, refract index of the medium is mu m, and same time t, how much distance it can cover, that is the length of the medium it cover by speed in the medium, speed of light in that medium, distance by speed formula. L in the medium, speed in the medium, we have one formula, V is equal to C by mu. Speed of light in any medium is equal to speed of light in vacuum by refractive index. That we can write C by mu of the medium. Okay. So that length. So you see, and how much time it take to travel L distance in vacuum, that is t time. Within the same time, how much distance it travel in a medium, that what we call optical path of a vacuum. Optical path of that medium when compared to vacuum. So what you can write, optical path, make it equal, these two both t are equal. So from this what you can write, L medium by C into mu medium is equal to L by C. From this optical path L medium is equal to, we can write, C get cancelled, is L by mu medium. Suppose you see, if you take a medium, of length L, refractive index is mu1, light enter into that, the wavelength of the light you can take it as lambda, the distance of two successive points. So first medium now you can take it as lambda 1. So that means how many number of waves are fitted in this L length? L is equal to number of waves N1 into length of each wave, that is lambda 1. Total length is equal to lambda into total number of waves inside the medium. Suppose for the same length, if you take other medium, length is same, but now wavelength changes. lambda 2 refractive index also changes, other medium. Then what you can write? For the same length, L is equal to N2 lambda 2. So in two different media, the distance of the medium or length of the medium is same. Then what is the number of waves fitted in that medium? What is the ratio of number of waves? That we can, these two are equal. So what you can write, N1 by N2 is equal to, we can write lambda 2 by lambda 1, which is, we know that medium from one medium to other medium, how wavelength changes means it is a reverse ratio of refractive index. Sometimes they give that number of waves in the first medium, they want number of waves in the second medium. By giving wavelength also we can calculate, by giving refractive indices also we can calculate. If refractive index increases, what happened to wavelength? That decreases. That's why you get a reverse ratio. But what about number of waves? Number of refractive index increases, wavelength decreases, so more number of waves are fit in the given length. In these two mediums, how many number of waves are different? That means number of waves differ from these two mediums. That you can write delta n. That what you can write, n1 minus n2. So if you know number of waves in the first medium, n1 minus what is n2 from this, we can write n2 is equal to mu2 by mu1 into n1. So from that, number of waves differed is delta n is equal to n1, take common, we can write mu1 minus mu2 by mu1.